seat. Okay, this is the fourth session with title Introduction to Fully Homomorphic Encryption, and it will be delivered by Dr. Benjamin Tan. The time is yours.
Thank you. So good afternoon, everyone. My name is Benjamin, and I'm here to talk about fully homomorphic encryption. And first, I'd like to thank the organizers for inviting me to give this talk. All right. So a brief outline to what we will talk about today. So we basically go through some brief introduction on the concepts of fully homomorphic encryption, and then talk about the construction roughly of the first generation of schemes. Then we see how the FHE evolved into its second generation, and finally we will look at how things have developed since then. Right, so homomorphic encryption, or HE for short, is basically an encryption scheme with some special properties. So the keyword here is homomorphic. So basically what it means is that the encryption function is a kind of like a homomorphism. So you can actually do meaningful operations on ciphertext. So for as an example, say you have an encryption of message M1 and an encryption of message M2. If you try to add them together, you can potentially get an encryption of the sum of the two messages. So this is like the homomorphic part. And we have a few different flavors of homomorphic encryption. The first one, which is called partial homomorphic encryption, is where the encryption function is some kind of group homomorphism. So you can do one kind of operation, be it addition or multiplication. And examples include the Paye encryption scheme or Al-Gamal. And then following that, we have something called the fully homomorphic encryption, where your encryption function is a ring homomorphism. So you can do both addition and multiplication. And additionally, we have something called a leveled variant. So in this leveled FHE, you can do a limited number of multiplications. So to get into the construction, we start with a very simple idea. So this is was from a work by Rives, Adelman, and Petrozos in 1978. So they tried to come up with a way to do this fully homomorphic encryption. At that time, they called it privacy homomorphism. So you start with a secret key prime P with some, like an operation key, n equals to P times Q naught. So this is like an RSA system. Then if you want to encrypt a message modulo ZP, you can try to do this. You encrypt by generating a random queue, taking P times Q, and then you add the message to it, finally taking modulo N. Then decryption is straightforward. You take whatever you got and you modulo ZP, you modulo P. And of course, if you try to do operations on them, you basically just do work on the numbers themselves. But unfortunately, this scheme is insecure, and so we have some work to do. Now, the first construction of FHE actually came about in 2009, so about 30 years since the Rives et al. Paper. And it was based on something called ideal lattices. But in the following year, Gentry, who gave the first construction, and a few collaborators, they came out with a nice, easy, straightforward, simple way to do FHE, so over the integers. So similar to the Rives et al. Work, you start with a prime P as your secret key, but now instead of your P times Q naught, you use something called a noisy RSA, let's say. So you have N naught equals to P times Q naught, but additionally you need to add Q times small E naught. And now your message space from ZP goes to ZQ. Then if you try to encrypt, you do very similar things, except now you add Q times E, where E is a small error. And when you decrypt, you take modulo P first, and then you take modulo Q to extract the results. Operations on the ciphertext are the same. You add and you multiply, and you do it modulo N naught. So now the security for this scheme is reduced to something called the approximate greatest common divisor problem. Basically, it asks you to find the biggest the biggest divisor of N naught, which is rather the approximate in this case, because we added some noise to it. And unfortunately, this scheme is not fully homomorphic in the sense that we cannot do arbitrarily many operations. And so now let's look at why. So when you try to decrypt, you will only succeed and get your correct message if the ciphertext has this form and the error is bounded by this term, P over 2Q. Basically, you need to make sure that QE plus M does not overflow modulo P. And so if we have encryptions of two messages, M1 and M2, like so, and we assume that the noise of each is actually bounded by B, then let's look at the noise of operations. So if you try to add, the noise would be roughly 2B, let's say. But when you multiply, the noise is much, much bigger. It's actually B squared. So if you do one multiplication, your noise goes from B to B squared. If you try to do more, so from B to B squared, B4, B8, and so on. So the noise actually grows exponentially in the number of multiplications you do. Okay, so now this is roughly how we would do consider homomorphic evaluation. You basically consider a tree where you do add and multiplies of your messages. And now we will just abstract it a little bit, and we call it algorithm eval that would take a function f, maybe represented this way, and your inputs, and give you some ciphertext C star. So if your inputs are bits, so meaning zeros and ones, then your function f can potentially be anything because of the property of Turing completeness, which is also why we call it fully homomorphic encryption, because you can do arbitrary functions with bits. So to solve this problem of noise growth, Gentry proposed this idea called bootstrapping. And this technique basically has this key insight. You can try to use the eval function to clean up ciphertext. So if you recall the decryption, you can think of it as so if you take the message, the ciphertext C star from the previous slide, if you try to decrypt that, you will get the function f on your inputs. So now if we let the function f be the decryption function, and your ciphertext be the encryption of your secret key, and you try to run eval on it with the C star previously, then you get some output C prime. And if we follow the logic, if you try to decrypt C prime, you should get decryption of secret key and C star, which is the function itself. So the idea is that if you have a noisy ciphertext that you cannot use anymore, and you have an encryption of your secret key, you can try to use the decryption function and get a new C prime that is less noisy and you can continue using. But unfortunately, doing this has its own problems. So now we need to add an additional assumption called circular security. Basically what happens is, here we have to encrypt the secret key with itself. And so we don't know if this is true for all schemes. And so we don't know how to prove that FHE schemes have this property so far. So we need this assumption. All right. So that's basically it for the first generation of schemes. So we managed to construct FHE with this nice idea called bootstrapping. And now we move on to the next phase in the second generation, where we try to construct FHE from lattices, more well understood, well studied hard problems. And we see some improvements in the way we manage this noise, and also this idea of single instruction, multiple data. So FHE from lattices began with Rakowski and Bakudanatan in 2011, and they based it on the learning with errors problem by Regev. So in that problem, you basically have you take a random A, random vector A, and you want to distinguish between these two tuples, A and B, and A and U, where U is uniformly random. So let's see how we translate what we know so far into this setting. So now your secret key, instead of a prime P, becomes a vector S, and your operation key is now just the number Q that is co-prime to big Q. And your encryption, so we change now we take a random vector A, and for the other part, we compute like the LWE problem. So the secret key transpose times A plus Q times the noise plus M modulo Q. Then for decryption, we basically try to remove this term by taking S transpose times C naught and subtracting it from C1, modulo Q and modulo big Q. Okay, so the previous one was like a proof of concept, but lattices on their own is actually quite inefficient. And so we switched to something called ideal lattices or structured lattices for more efficiency. So now this will appear in 2012 under Brachowski, Gentry, and Van. And the problem is under the ring learning errors. So now instead of a random vector, we use a polynomial from some ring. In this case, the ring of ZQX modulo phi mx, and phi mx is the cyclotomic polynomial. Then now the problem becomes to distinguish two polynomials, A and B, where B is constructed like this, and A and U, where U is a uniformly random one. So small changes, instead of the secret key, vector, now you have a secret polynomial. And instead of taking the transpose and multiplying it by the first term, now you just do polynomial multiplication everywhere. Okay, so addition is pretty straightforward. If you look at this, if you have A and AS plus QE plus M, you try to, if you want to add two ciphertexts, you just add them component-wise, and the same kind of a structure will hold. But multiplication is a little bit more complicated. So if we try and look at the decryption function, you basically compute C1 minus C0S. Now if you want to multiply two messages, so say we multiply their decryption procedure, then what we see is this term, and if we break it down a little bit, like this. So you have C0, C0 prime, C0, C1 prime, C1, C0 prime, and C1, C1 prime. And if you think about what are the terms of S that are multiplied by them, it's S squared minus S and 1. So in a sense, now to try and multiply ciphertext, you end up having to construct something a little more complicated, from 2 terms to 4 terms. And if you try to do this again and again, it's just going to blow up 4 terms, maybe 16, and so on. So it's not very nice. So a key idea to control this is called key switching. And the technique involves using encryptions of a secret key S squared. So what happens is you try to transform this term, C naught prime, then you need to multiply by S squared, into something which we just call C double prime. And now C double prime, if you multiply by S, will give you something that's roughly the same. So if you do that, we can get a nice ciphertext again. So now 2 terms, C0 star and C1 star, unlike the previous one where we had like 4 terms. And so if we multiply and we do key switching, we get this back. We can do another step, blow it up, switch it down, and we will always be having nice ciphertext. We avoid the blow up. Okay. So that was multiplication for ring LWE schemes. So the next problem would be noise management. So previously, in the first generation, our noise blew up like this. It just exponentially. So in the same work, Brachowski et al., they came up with this idea of modular switching, where you scale your prime Q, your number Q, to a smaller number, Q prime. Basically, dividing by B, which is the error term bound. Then, if you do this scaling, your noise, which is of magnitude B squared, now drops to magnitude of B, but your moduli becomes smaller. So what happens is, if you want to do L many multiplications, you need about maybe L plus 1 many such numbers, and every time you do a multiplication, you drop down by 1 step. Alternatively, Brachowski came up with this idea of scale invariance, where he said, instead of encrypting the way we do, let's change it up. We scale the message instead. We put the message at the higher order bits. And then what happens is after multiplication, we divide by q, small q over big Q. And what happens is your noise now doesn't become quadratic. It only increases by a factor of k, which is related to your ring dimension. And if you set Q like this, where you put this factor L plus 1 times, then you can roughly do L levels. So in the second generation, what we achieve is level FHE, meaning we can do a limited and predetermined number of multiplications without the need to bootstrap. So previously, if we had this kind of growth, if you want to have, say, 10 levels, you either need to make sure your parameters were large enough, or you try your best to, you bootstrap, and then you do it 10 times. Then you can do 10 multiplications. But now, you can just simply set your parameters nicely, and you can do L multiplications. Okay, so in this last part, we talk about how we pack. So we want to put multiple data into one ciphertext, so that when we do one operation or single instruction, we do it on all those data that we pack together at the same time. So if we look at our plaintext space structure, so first thing, we are using a modulo Q. So in that modulo Q, the cyclotomic polynomial actually factorizes into smaller terms of degree D, and there you'll find L many of them. Then your plaintext space, which is actually R cubed, like this, actually is equivalent to, or isomorphic, let's say, isomorphic to a product of finite fields. So now, instead of packing one bit or one FQ element, you can actually pack a vector of L many FQ to the D elements. And when you add them like component-wise. When you multiply by component-wise, simultaneously over all of them. But not only that, actually, we can do more with this packing method. So if you consider the automorphisms of the cyclotomic polynomial, you can actually do interesting things like Frobenius automorphisms, where you send an element x to its cube power, and you can do rotations and shifts. So say you have an element here, you can do a rotation that lets it interact with an element maybe 3 slots down. These kind of things. And these techniques are enabled by key switching. So what happens is you basically just transform your ciphertext by raising it to the power of kappa for some kappa. Then your secret key will actually correspondingly change. And then you apply key switching to get back something that the original secret key. So the main idea is that whenever you do something such as multiplication, or in this case, automorphisms, your secret key will change, but we can use this idea of key switching to always go back to the original key. Then we don't have to worry about, you end up having complicated powers of S if you don't have key switching. Okay. So roughly that's how FHE evolved over the first, let's say, 4 years. And now we look at how we use the second generation. So the first thing that we look at is something called approximate numerics. So if you try to do exact arithmetic, so integer operations, add and multiply, or rather in this case fixed point. So if you start with numbers with only 3 digits in their decimal place, you try to multiply them, you see that the number of decimal place actually increases with each operation. And if you want to work in FHE with like this, you first have to scale all of these to integers. So let's say 1, 2, 3, 4 now becomes 1,234, and so on. And you do your operations. And what happens is, if you think of the number that you need to put in front, subsequently here, say this is 1,000, then this becomes 1,000 square, this becomes 1,000 to the 4, and it blows up, just like how noise blew up in the first generation. So this means that if you want to do operations with exact numbers, you end up needing to put a very, very large modulus so that you can capture the results, that they don't overflow. So first, we recall what the encryption scheme looked like. So in the previous slides, we had this method where we take m plus q times e. So it looks like this. This is the Brachowski-Gentry by Kuehne-Nagel scheme. And or we had the scale invariant version where you put small q over big Q times m plus e, which looks like this. So B is for Brachowski and FV is Van Vercauteren, another paper that deals with this. So in 2017, so quite recent, John et al. Proposed a new way to try and do FHE. So they said, all right, we strictly separated the noise from the error, and we could do operations modulo Q. So let's change it up. We use real numbers, which we scale by some factor, and we just add the noise in and mix them together. So roughly it looks like this. Your message being scaled takes up this box, and your error is here, which is, and they are mixing instead of here where it's a hard gap. So what this enables is what you can think of, how you can think of it is you're encrypting your message M with like k bits of precision, meaning how many digits are accurate, and then E you add behind saying that, all right, we treat this as like an approximation of what we actually wanted to encrypt instead. So what happens is with this we can actually manage the scale factor instead of delta, delta square, and so on. If we do a scaling operation after multiplication, then this delta square term that we get when we multiply stuff, it becomes delta again. And your noise also reduces correspondingly. But in this case, the new noise is definitely bigger than the old noise. So the result is that your messages still lose some precision. So previously, maybe they were accurate up to the third decimal place. Now they might be accurate only up to the second. And so roughly the picture for how CKKS works is like this. So this is your original encryption. If you do a multiplication, you scale, so your box becomes smaller, your error becomes slightly bigger. And if you multiply again, your box becomes smaller, the error becomes more. So if you look at, this is the part where you can say that your message is correct, like the digits are the same. So after each operation, you get fewer and fewer. And like in real terms, it will probably look something like this. So this was what we saw originally. Now if we use the CKKS method, essentially we have this kind of effect. We can bound the number of digits that we use, but you start to see that the numbers get a little bit off at the end. So here, 45.673 becomes 45.663. Okay, so in CKKS, we can also do some kind of packing, but it is different from how we did it originally. Because now the plaintext space is not ZQ, so there's no modulo Q here. You are working with integers. So we first use this notation, well, Zm star being integers in Zm that are co-prime to M. Then the M cyclotonic polynomial, we know factorizes like this. So here zeta M is the primitive M-fruit of unity. Then we use this relationship to encode plain text instead. So if you have a bunch of plain text xi, in this case we can actually pack even complex numbers. So we're not restricted to the rails anymore. So what we do is first we find a nice polynomial over the rails, such that when you evaluate it at the roots of unity, you get your xi. So this process is called the discrete Fourier transform. Then we scale these coefficients by the desired scale factor, and we do a rounding to get an integer. So what happens is with this mx, if you evaluate it at the roots, originally with mu you get exactly xi, but because you did some scaling and rounding, it's now approximately xi. And as with before, the rotations and shifts are possible too, and you use the key-string technique for that. Okay, so we said approximate numerics was the topic of this section. So basically, why we call it approximate numerics or approximate numerical computation. So first off, when we encrypted, we already said that we were encrypting an approximation of what we originally wanted. And from here, we can do addition and multiplication. So we could evaluate polynomial functions. But we can actually do more. We can do some we can do, well, not some, probably most non-polynomial functions like inverse, exponential, or the hyperbolic tangent. And how do we do that? We actually use the Taylor series as an example. So we know that e to the x has this Taylor series, at least close to, when it's close to x is close to 0. So you can truncate this series at any point and approximate the function that you want to evaluate. So note that if you use the Taylor series, these approximations are only minimizing the error at a particular point. But in general, you can actually do this kind of technique. You can approximate what function you want to evaluate by some polynomial. And there are various ways to do it. So amongst them, we have Chebyshev, min-max, and least squares approximation methods. So all these give you some polynomial that would roughly correspond, that would roughly be equal to whatever you wanted to evaluate in the interval of your choice. So this scheme is very popular now because of its applications to machine or deep learning, if you're aware of that. So this CKKS scheme can let you do approximate fixed point arithmetic on encrypted data with native support for polynomial functions. And with the Taylor series or polynomial approximation techniques, we can do approximate analytic functions, approximate neuron activation functions, such as the sigmoid hyperbolic tangent. And so this is being widely applied, especially in this competition called the I-dash competition, where they try to do privacy-preserving genome analysis. So the idea is that you have algorithms and techniques that let you analyze some information of genome. And now this competition asks you to do it with encrypted data. So you use homomorphic encryption to encrypt your genomic data, and you run your algorithms on them, on this encrypted data, probably using CKKS these days. So in the 2017 competition, the CKKS scheme could do logistic regression in 10 minutes and was best of that year. And then in the next year, in 2018, everybody switched to using this scheme. So it just shows you how powerful the ability to do some approximate numerical computation on encrypted data is. Okay, so that's roughly it. So another extension, another development, this one was done mostly by me and my collaborators. So we tried to use the finite fields that were the plaintext space or BGV. So the traditional way of computing on encrypted data with the SIMD approach, you just take a bunch of bits and then you compute Boolean circuits on them. So it's kind of wasteful when you know that your field, the plaintext space is actually FQ to the D. And so we try to use this in this approach. So let's say FQ to the D can be represented this way. A0 plus A1 all the way to AD minus 1, T to the D minus 1, modulo FT, where FT is irreducible and of degree D. Then you can look at this like an FQ vector, and we can encode numbers. So how we encode numbers? We take base or radix Q representation. Essentially, you have your number, and you consider it in this fashion. You replace Q by the indeterminate, and that will be how we encode numbers. Then the question becomes, what can we do if we encode numbers this way? So in the so-called the pioneer work in this direction was by Kim et al., where they considered how to do equality. So how could you compute if you have two numbers, x equals to y, encrypted form? So in this case, they tried to do this by using the field element encoding, and they applied Fermat's-Little theorem or Lagrange theorem in general. So what this theorem says is, if you have any non-zero field element, if you raise it to the cardinality of the field minus 1, you will get the 1. So from this idea, if two numbers x, y are equal, it means that their encodings will be equal. Then if you subtract their encodings and raise it to this by Fermat's-Little theorem, you will get 0 because if x and y are the same. So basically, we get a nice little equality test with this formula, 1 minus fx minus fy to the qd minus 1. And it's actually pretty efficient. So because we could use Frobenius automorphisms, we actually only need logarithmic in the degree number of operations. And from my experiments, we found that we could do this in 2.6 milliseconds amortized time for 64-bit numbers, which is like what we use in our computers these days. And then from there, it's natural to think what other kind of relations can we do. And in another line of work, we consider order. So for order, there are 4 types: less than, greater than, less than equals to, and greater than equals to. So all of these actually can be represented in terms of one function, less than. So like this. So if we now just need to focus on the less than function. And if you think about how to do it, in the previous approach, we found some polynomial. So if we were to do the same thing for less than, we try to construct one, say using Lagrange interpolation. It is actually quite inefficient because now you have your field being fq to the d, so there are q to the 2d possible inputs. That means your polynomial will have exponential in d degree. So what we try to do is to look at how people were already doing it, which was basically the Boolean circuit approach. So in the Boolean circuit, which we generalize a little bit, so now we consider radix q instead of just 2. And you have your digits x0 to xd minus 1 and y0 to yd minus 1. So d minus 1 being the most significant and x0 being the least. So the idea is that for these circuits, if you compare the most significant digit, if that of x is smaller than y, then it means that the numbers themselves are smaller. And for any other digits, if they are less than, and every other digit in front of it is equal, then it means that the numbers are less than, x is less than y. If none of the conditions here are fulfilled, it means that it's the other way around. Okay, so here basically we are doing O of D work because we have D steps, and in each step we do a constant number of things. And we have these 2 problems. First is, if you do it with the polynomial method, you need exponential in the degree operations. But if you try to do this technique, the circuit technique, you need to be able to access each individual digit. So the x0s, the xi's. So to solve this, we can actually make use of the structure, the algebraic structure of the plaintext space. So fq to the d is a d-dimensional vector space. So if we represented this like this just now, so we can consider projection maps on linear vector spaces. So if you try to project the ith coordinate to the first one, that's an fq linear map. And what we know by theorem is that these fq linear maps actually correspond to some polynomial called q polynomials. So q polynomials are special polynomials of this form where the powers of x are only some power of q. So this kind of polynomials we can easily evaluate using Frobenius automorphisms because so this one a1 times xq is basically one Frobenius automorphism. ad minus 1 times x q to the d minus 1 is like d minus 1 many automorphisms, let's say. So when we try to implement this in practice, we see performance of about 152 milliseconds for 64-bit numbers. So if you look at the performance of these things, you see a very big gap. Equality is really, really fast compared to order, at least 50 times. And if you look at the amount of time it actually took to run the whole thing, the difference is also pretty big. So how can we improve this? Basically, there are 2 ways. First, we did not use this packing approach, so we should try to use it to make things faster. And second, since this is O of D, it means that running time depends on D. So if we reduce D, we should get something faster. So what happens is that we propose this idea called the vector of field elements approach, where you do a two-level decomposition. So instead of breaking down your numbers directly into FQ digits, you first break them into some middle-sized digits. So let's say we use base Q to the H. Then by this factorization, we have W many digits. So in this case, the digits, we just call them BXJ. So this is where you can see the breakdown. And pictorially, it corresponds to this. So if this is your original number broken down into digits, you basically take the first H of them, you put them in one rectangle, the next H, and you put them in rectangles, and so on. Then when we do the projections, because of single instruction, multiple data, SIMD, we project them simultaneously. So, well, because we want to use SIMD, so we encrypt this as a vector. So one ciphertext stores this thing. So to actually compute the algorithms, we actually just use the previous techniques that we highlighted. So we will apply equality tests and less than tests on each individual ones. But because of SIMD, we just need to run it one time. So in this case, to work with these digits, we use the same principle as before. If your middle-sized digits are smaller, the most significant one is smaller, then the whole number is smaller. Otherwise, you look at the intermediate ones. If any one of them is smaller and the rest above it are equal, then it is also smaller. Otherwise, it's the other way around. So when we do this, now D becomes H, but we add on a few other operations where we have to compare these BWs, or rather these BIs. So we add a log W there. And equality is straightforward. So if you want to know if two numbers are equal, you just check that all their digits are equal. All right, so how this translates in real time, in performance. So equality is slightly more expensive now, but we managed to reduce the running time of order by about 4 times in amortize, and the total time here is about 3 times faster now. So what happens is we have to sacrifice some equality, but we get a very significant improvement in the performance for order. And if we look at the traditional approach, so instead of bits, let's say we encrypt them as elements in ZQ, you need like, let's say, 50 milliseconds to do any meaningful operation. So for this approach, we are looking to try and apply it to database operations or decision tree evaluations, and we want to extend this to other functions too, such as addition and multiplication, so arithmetic and maybe even other things. So some interesting things to think about are there any better ways to use finite extension fields besides the projection maps? And what if we try to use a ring instead? Instead of the field, we use a ring of similar number of elements. Whether we can do something with it. Okay, so lastly, to round off, I just touch on what happened after the second generation. So in the third generation, which happened in about 2013, it uses this concept called a gadget vector, which is very important in lattice cryptography. So you have the gadget is basically this vector G of elements, entries 1, 2, powers of 2 all the way to floor of log Q. And you have this function G inverse, which is basically binary decomposition. So if you have any ring element M, if you take the inverse of M and you multiply it by G, then you get back the number, the M itself. So just a brief sketch of the third generation scheme, which is by Gentry, Shahai, and Waters in 2013. So now you encrypt your message here. You use this G instead of having some error Q or some scale factor. And here you have your LWE part. So the nice thing about this is that if you try to multiply your ciphertext, you basically take your So say you want to multiply two ciphertext C1 and C2. So you take the decomposition of one of them and you multiply it to the other one. You don't have to do anything fancy. So there's no need for key switching or modular switching. You just need to do some binary decomposition. So this means that you only need public keys, secret keys, no other additional objects in your encryption scheme. And this actually lets you do more interesting things like identity-based or attribute-based FHE. So I don't know if you guys know what these are, but in identity-based systems, basically you can encrypt just by knowing someone's identity. And then only the person whose identity you use to encrypt can do decryption. And attribute-based is a more general form where instead of an identity, you have a series of attributes. And only if you have the correct attributes can you do decryption. So the key innovation for the third generation FHE schemes is this idea of high performance bootstrapping. So if you think about it, what's the smallest FHE system that you can produce? Is basically one operation and followed by bootstrapping. Then the question becomes, how fast can we do bootstrapping for this model? So in 2015, Lucas and Michiancho proposed this idea of a homomorphic accumulator that lets you do really fast decryptions. So decryption here, this is the LWE version of decryption, not the ring one. And so what happens is they said, all right, this third generation GSW scheme, we can use the ring version and do some really nice things. We can encode in the exponent of elements, and then multiplication becomes addition. So you can imagine that this function, which is a multiplication of bits, so you are selecting and then adding things. So selecting is done very easily. By adding, you replace with multiplication, and then you add a new additional technique to extract clean ciphertext out of this system, and you have a really fast FHE scheme. So in their work, they showed that they could do this in less than 1 second. So what does it mean? You can do one Boolean gate, be it AND, XOR, NAND, and then bootstrapping. Less than 1 second, and this was subsequently improved in the next year to less than 0.1 seconds. Right. So roughly, this is what we went through. And so I just want to end off with a table first. So basically, we have three main paradigms for homomorphic encryption now. We have the classical one, which uses the second generation schemes. We have the approximate computation model, which uses the CKKS scheme from 2017. And we have the high performance bootstrapping technique that uses the Chilotti et al.'s work. And all these are practical in the sense that you can find C++ libraries implementing this, and you can actually play with them. And we also seen there were competitions that were trying to use these libraries to do real work, meaningful work. So some last comments. So the numbers that I gave, they were for CPU, or in the order of seconds mostly. But a lot of work is being put into hardware acceleration using GPUs and FPGAs. And we will expect to see 50 to 100 times. So some of this work has already been done, and the numbers of amount of improvement we can expect. And so this homomorphic encryption has a very wide set of applications, of which machine and deep learning is very trendy. A lot of papers have been published in the last few years. And, but there are still many challenges in this area to be solved. And many big companies are working in this space, including Microsoft and IBM. And something to introduce to you guys. So there's an ongoing standardization effort by the community involving the US government agencies, some companies, and the academic institutions to try and standardize and make HE more usable by everybody. And you can find the details at this URL. Okay, so that's the end. Thank you very much, and happy to answer any questions.
Thank you, Dr. Benjamin Tan, for the lecture today. And please stay on the stage. We will give you a souvenir as a speaker for the lecture today. May I invite Dr. Sutopo to come on the stage and hand over the souvenir to the speaker. Give an applause to Dr. Benjamin Tan. This is the end of our agenda today, and thank you for your participation. See you tomorrow.